This is the second video about rate laws. In the last video, we talked about what a rate law is and what the different parts of it are. And in this one, we will look at a data set and talk about how to derive a rate law from a data set. So the last thing we talked about in the last video was that all rate laws are experimentally determined, and they come from data sets that look like a variation in the reactant concentrations and then measurements of the initial rate. And we can use that data to solve for the rate constant K and the reaction orders, those exponents above each of the different reactions. And just to preview what that might look like, we can think about how changing the order of a reactant would change the rate in a certain way. So let's say we have some generic reaction rate equals rate constant times X. We think about if the exponent for X was 1, if we multiplied X by 2, that would multiply the rate by 2. Or if we had X with an order of 2, if we multiplied X by 2, it would multiply the rate by 2 squared by 4. Or if our rate law looked like this, rate equals K times X to the 0, no matter what we do to the X, the rate is always going to stay the same. So I guess that would be like multiply by 1. So this is what we're looking for. We're looking at how the change in the concentration changes the rate to let us predict what those reaction orders are going to look like. Okay, let's get some data. Here is the data table for our problem. I will pause here so that you can copy this down into your notes. Okay, we're back. So this is going to be finding the rate law from the raw data. So what we have here is an example reaction with a mercury 2 chloride and a carbon oxygen compound called oxalate. And those two things decompose to form chloride ions, carbon dioxide, and a mercury 1 chloride. And just like we said in our plan, we have taken the concentration of these two things, and we've done a couple of different combinations of concentrations. And then we have a list of measurements of the initial rate for each of those conditions. And we need to use the rate law, use the data given to find the rate law. So let's plan our strategy first before we do anything too fancy. We know we need to find the rate law. So let's review what a rate law looks like. So it looks like rate equals rate constant K times each of the reactant concentrations. So times mercury chloride to some exponent and times oxalate to some exponent. And we know from our previous page that we need to find the rate constant and each of the individual orders. So we have 3 different variables to find. So we're going to have to do 3 systems of equations to find them. And the way we're going to find each of these variables is we're going to set 2 of them to cancel so that we can solve for 1 of them at a time. We can use what we know about rate laws to do that. We know that no matter which one of these trials we're doing, the K constant is always going to be the same. As long as it's the same temperature, the K is the same for a particular reaction. And we also know that this exponent is going to be same for everything. And if we take 2 trials that have the same concentration, we can get that exponent to cancel. So our general strategy is going to look like this. We're going to write the rate law for situation 1. So we'll call this rate 1, concentration 1, concentration 1. Then we're going to write another rate law for situation 2. Rate 2, same rate constant, concentration of mercury chloride 2, concentration of oxalate 2. And we're going to make a ratio of those 2 situations, and then we're going to set it up on purpose so that we should be able to cancel our rate constants because they're always the same. We're going to pick one variable at a time to solve for, and then all of the other concentration variables we're going to cancel out. By making sure we choose values for concentrations that are equal to each other. We'll cancel out all the other terms, and all we should be left with is one ratio of the rates and one ratio of one concentration. And then we only have one unknown, and we can solve for that one unknown variable at a time. I think this will make more sense as we get going. So we have decided to define M as the coefficient for the mercury compound and N as the coefficient for oxalate. So make sure if you use a variable, you write somewhere on your paper, you indicate what that is, so your poor professor is not confused. So when we want to solve for M, we want to keep this term, and we want the oxalate term to cancel. So we need to choose two trials to use where the oxalate concentration is the same so that this term cancels. So when I look at the oxalate concentrations, I see trial 2 and 3 have matching values for oxalate. So I'm going to choose those two. I'm going to choose row 2 and row 3. Okay, so now we're going to set up our rate law ratios. So the first thing is the rate. That's over here. So for trial 2, the rate is 7.1, 10 to the negative fifth. And for trial 3, the rate is 3.5, 10 to the negative fifth. Equals. The next part of the rate law is the rate constant, K. They both have the same rate constant. Then we have the mercury chloride concentration, which is 0.105 for trial 2 and 0.052 for trial 3. And each of these terms should be raised to the exponent m. But the way exponents work is if all members of the fraction are raised to the same exponent, we can just write one exponent for the entire fraction. And that one's a little bit neater and easier to solve mathematically. So rate constant, mercury concentration, and oxalate concentration. So the oxalate concentration is 0.3 for both of these trials. And again, both of them are raised to the n exponents. So we can just raise the whole thing to the n exponent. So now we should be able to cancel some of this stuff if we set it up correctly. So k over k will cancel, and 0.3 to the n over 0.3 to the n cancels. So all we have left is this fraction for rate and this fraction for one of the concentrations. So we can plug that in to our calculator, and we should discover 7.1 over 3.5 is 2. And 0.1 over 0.05 is 2. And don't forget the exponent, because we still don't know the exponent 2 to the m. Okay, so now all we have to do is solve for m. So the easiest way to solve this for me is to say 2 times how many other 2's will give me this. So in this case, 2 to the 0 power would be 1, 2 to the 1 power would be 2. So our m coefficient is going to be equal to 1. Sometimes this is easy enough that you can solve it in your head, and sometimes you may need to use your calculator. Solve is what we did there. Okay, so we've got one coefficient. Now we need to find the other coefficient. We are going to solve for all the coefficients first. Okay, when we want to solve for the oxalate coefficient, we want all the other concentrations except oxalate to cancel. So we want to find a set of trials to use where the mercury has the same concentration. So the mercury has the same concentration for trial 1 and trial 2. So I'm going to pick those. In some cases, if your data table is big enough, there may be more than one correct pair that you can choose, but in this case, there's only one pair to choose for each. All right, so I've chosen my two conditions. Now I'm going to set up my rate fractions. So the rate for row 1 is 1.8 times 10 to the negative 5th. And for row 2, 7.1 times 10 to the negative 5th. Then we've got our rate constants. And since we know that they're going to cancel, I'm just not even going to write it this time. I know this is going to cancel. And I picked out a concentration of M so that I know that's going to cancel. And I'm going to skip straight to N. N in row 1 is 0.5. N in row 2 is 0.3. That whole fraction is raised to the N. Again, these terms ended up canceling. Okay, now we'll simplify. You may or may not be able to do this one in your head. 1.8 over 7.1, that is 1/4. And 0.15 over 0.3 is 1/2. And that is raised to the N. Don't forget the exponent. And then we'll solve for N. And again, 1/2 to the 0 power is 1. 1/2 to the 1 power is 1/2. 1/2 to the 2 power is 1/2 times 1/2, and that's 1/4. Feel free to use your calculator if you need help. Okay, so now we have got 2 out of our 3 variables. We've got both of the orders. We just need to find the rate constant. So let's write our rate law with the new numbers that we know. So rate equals, still don't know the rate constant, times mercury 2 chloride to the first, because we know that now, times carbonate to the second, because we found that now. So we've got 2 out of the 3, and K is left. And we can even, for bonus points, write the overall order just to prove we know what that is, which is the sum of all of the exponents, which is 3. All right, so now we still need to find for one more variable. So what we're going to do is we're going to pluck any row we like out of the table and plug in the 3 values for the concentrations and the rates to solve for our K unknown. So it absolutely does not matter which row you pick. I'm just going to pick the first row, and I'm going to plug those numbers in. So the first row rate is 1.8 times 10 to the negative 5th equals, K is what we're solving for, the mercury chloride concentration, 0.105 to the first, and the oxalate concentration, 0.15 to the second. Make sure you keep those exponents in here. If you lose that exponent, it's going to be a super duper different looking answer. Okay, so we'll solve for K. And you and your calculator should reach an answer of 0.00762. So that is our third missing number. So to finish the problem, we need to write the completed rate law. So rate equals our rate constant, 0.00762, times the mercury chloride concentration to the first, times the oxalate concentration to the second. Ta-da! We figured out that entire rate law just from these 3 lines of data. So that was pretty cool. I'm pretty impressed with us for figuring out all the information about the rate law just from a little data table. And there's one more thing I want to address, and that is the fact that I left a super big box for K because I didn't list the units for K. So let's just take 2 minutes to talk about how to find the units for K. So We know the units for the other pieces that are involved in a rate law. So let's start with what we know. So the unit for the rate we have seen is always the same. It's always in molarity per second, or minutes, or hours, or years, or some unit of time. So is molarity over some unit of time. We know the unit for concentration because we've been using that for 2 chapters now. That is molarity, moles per liters. So that only leaves the rate constant. And the unit for the rate constant depends. Basically, our rate constant is our fudge factor that we introduce into a proportional to relationship to make both sides equal. So we're just going to use whatever unit we need to cancel out all the other units. So the units are the same on both sides. Oh dear, it is difficult to read. There we go. Cancel out other units. So let me give you an example. We'll do the one we just finished. We can figure out the units for that one. So the problem we just finished said rate equals 0.00762 times mercury chloride to the first times oxalate to the second. All right, so let's put in the units that we know. I often just write a totally separate rate expression with units. So the rate units were in molarity per minute. Trying to find this. This concentration is molarity to the first. This concentration is squared, so the molarity is also going to be squared. And then we need to find the unit for the rate, something that cancels out and makes both of these 2 sides equal. So we see that there's a minute on the denominator in this side, so there has to be a minute on the denominator in this side because neither of the other terms have time in them. And then the right side has molarity to the third, and the left side only has molarity to the first. So we need to get rid of 2 of the molarities from this side. So we'll put 2 molarities in the denominator. If you don't like the way that looks, if you want to write molarity as moles per liter, you can also write it as liters squared per moles squared per minute. Also an acceptable answer. Units. So let's go back and add in the appropriate unit. 1 over minutes. Oh, I didn't leave a big enough box. We tried. Okay, one more example just to prove to you that it does in fact depend on the order of the reaction. Here's another one. Here's our rate law from earlier with the peroxide. This one is a first order reaction. First order reaction overall. So our rate could be in molarity per second. And we only have 1 concentration, so that's m to the first. And we need to multiply them by something that makes both sides equal. So we're always going to have time in the denominator. And then we have 1 molarity on this side and 1 molarity on this side. So the units for K are just 1 over S. We don't even have a molarity in that unit. So just watch out, the units for K will change depending on what the order of the reaction is. You'll just have to wait and solve for that at the very end. So that is everything about rate laws and rate constants and finding a rate law from data. The next set of videos will be about integrated rate laws.